14. Measurement and effects of heat. Revision. We know that to perform any sort of work, energy is required. Energy exists in different forms. Last year we studied heat, a form of energy, in detail. We learned that heat can flow from one place to another, which is called transfer of heat. Heat is transferred by different modes, namely conduction, convection, and radiation. We studied that the state of matter changes due to heat. Solids like copper, iron are good conductors of heat, while wood, plastic are bad conductors of heat. We also studied about expansion and contraction of solids, liquids, and gases due to heat. When we give heat to an object, it expands and it contracts on cooling. What else did we learn? Can you recall? Yes! We also studied the construction and function of a thermos flask. In continuation to this, today we are going to study about measurement and effects of heat. Come then, let us begin. Concept and unit of heat. Let us do an interesting exercise. Some events are shown here. Let us observe them and find out what do they depict. In the first event, a vessel containing water is kept on a gas burner, and due to heat, water is seen boiling. Here, liquid is turning into gas. In other words, the state of matter is changing due to heat. In the second event, we can see an ice cube kept in a dish melting because of heat present in the surrounding. In this case too, state of matter is changing due to heat. Next, in the third event, striking the coated end of a matchstick against the striking surface of a matchbox is producing heat energy. Here we can say that chemical energy is getting converted into heat energy. In the fourth event, a hot air balloon is rising up due to expansion of air caused due to heat produced during combustion of fuel. In this case, there is an application of one of the effects of heat. After this exercise, come, let us now proceed further. We have already studied that heat flows from one object to another. But do you know which factor determines the direction of flow of heat? Temperature difference determines the direction of flow of heat. Heat flows from an object at high temperature to an object at low temperature. Temperature of an object tells us how hot or cold that object is. The temperature of a cold object is lower than the temperature of a hot object. Thus, the temperature of ice cream is less than the temperature of tea. Come, let us know the unit of heat. The unit of heat in SI system is joule, while that in CGS units is calorie. 1 calorie is equivalent to 4.18 joules. 1 calorie heat is the heat required to increase the temperature of 1 gram of water through 1 degree Celsius. Come, let us now solve some numerical problems. Solved examples. 1. how much heat will be needed to raise the temperature of 1.5 kilograms of water from 15 degrees Celsius to 45 degrees Celsius? Give the answer in calories as well as in joule. Let us first note down the given information. Mass of water is equal to 1.5 kilograms, which is equal to 1,500 grams. Change in temperature is equal to 45 degrees Celsius minus 15 degrees Celsius. We need to find out heat required for temperature change. We know that heat required for temperature change is equal to mass of water expressed in grams into change in temperature expressed in degrees Celsius, which is equal to 1,500 into 30, which is equal to 45,000 calories. We know that 1 calorie is equal to 4.18 joules. Thus, 45,000 calories of heat is equal to 45,000 into 4.18 joules, which is equal to 1,88,100 joules. Thus, heat required for temperature change is 45,000 calories and 1,88,100 joules. Let us solve one more example. 2. If the temperature of water changes by 10 degrees Celsius on giving 300 calories of heat, what is the mass of water? Answer. Let us first note down the given information. Amount of heat given to water is equal to 300 calories. Change in temperature is equal to 10 degrees Celsius. We need to find out mass of water, that is M. We know that heat required for temperature change is equal to mass of water expressed in grams into change in temperature expressed in degrees Celsius. Substituting the given values, we get 300 is equal to mass of water into 10. Thus, mass of water is equal to 300 divided by 10. Therefore, mass of water is equal to 30 grams. Before solving numerical examples, we observed few events. Here they are again. Observing all these events, it is very clear that in each case, the source of heat is different. Come, let us then know about various sources of heat in brief. Sources of heat. Sun is the biggest source of heat received by the Earth. A tremendous amount of heat energy is generated due to the nuclear fusion taking place inside its center all the time. In the process of nuclear fusion, hydrogen nuclei fuse together to form helium nuclei, releasing a large amount of heat in the process. Some of it reaches the Earth in the form of light and heat. Next source is the Earth. The temperature at the center of our planet, that is Earth, is high. Thus, the Earth is also a source of heat. This heat is called geothermal energy. Next is chemical energy. When fuels like wood, coal, petrol, etc. burn, a chemical reaction takes place between the fuel and oxygen. Thus, in these reactions, heat is produced. Next is electrical energy. In our daily life, we use several equipments like electric press, electric heater, which produce heat with the help of electricity. Thus, heat energy can be generated using electrical energy. Hence, electricity is a source of heat. Next is atomic energy. A huge amount of heat is produced in a very short time when the nuclei of some heavy elements like uranium, thorium, etc. undergo reaction called nuclear fission. This is used in atomic energy projects like power plants based on atomic energy. Another source is air. A large amount of heat is present in the air around us. After knowing the sources of heat, let us now proceed to learn about the term temperature in detail. Temperature. How do we decide whether a substance is cold or hot? We normally use our sense of touch to decide the hotness or coldness of a given substance. But every time we cannot rely on our sense of touch on all occasions, especially when precision is required. Sometimes we may go wrong also. To know more about it, let us do a simple activity to prove this. Let us take 3 balls and mark them as A, B, and C. Now let us take hot water in ball A, lukewarm water in ball C, and cold water in ball B. Now let us immerse the right hand in ball A and left hand in ball B for a minute. After a minute, let us immerse both hands in ball C simultaneously. What do we feel? Yes, even though both the hands are dipped in water in the ball C, that is water at the same temperature, the right hand finds the water to be cold, while the left hand finds it to be hot. This is because the right hand, which was immersed in hot water for some time, finds the lukewarm water cold, whereas the same lukewarm water feels hot for the left hand, which was immersed in cold water. This indicates that the terms hot and cold are understood in relative context only. This activity proves that we cannot determine the temperature of an object accurately by simply touching it. Also, we may hurt ourselves by touching very hot or very cold objects. Therefore, there is a need of some device for measurement of temperature. Thermometer is a device for measuring temperature. In the previous grade, we studied about thermometer. In this lesson, you are going to learn about the construction of a thermometer. But before that, let us first know what is the difference between the terms heat and temperature. Heat and temperature. Before discussing about these terms, it is important to know what are potential and kinetic energies. Can you recall? Correct. The energy stored in an object is called potential energy, and the energy obtained from the motion of an object is called kinetic energy. Come, let us now know the difference between heat and temperature. In the previous grade, we learned that a substance is made of atoms. Atoms in a substance are always in motion. The total kinetic energy of the atoms in a substance is a measure of the heat contained in that substance, while the temperature of a substance is related to the average kinetic energy of atoms. Suppose the average kinetic energy of atoms in 2 objects is equal. Then their temperatures will also be equal. The motion of atoms in a gas at high and low temperature is shown here. If you observe carefully, you will notice that the atoms are shown with arrows. Length of arrows is different in both the cases. The direction and the length of the arrows attached to the atoms show the direction and magnitude of the velocity of the atoms. Thus, it is clear that the velocity of atoms in the gas at higher temperature is larger than the velocity of atoms in the gas at lower temperature. Let us now have a look on the motion of the atoms in a solid substance. The atoms in a solid object are tied to one another because of the forces acting between them, so they cannot be displaced from their places. However, when heat is supplied to solid substance, the atoms in it oscillate around their fixed position. Their velocity of oscillation depends upon the temperature of the solid. Higher the temperature of the solid, faster is their velocity of oscillation. Come, let us now compare the heat content of two objects. Suppose A and B are two objects made from the same material, and the mass of object A is twice the mass of object B. This means that the number of atoms in object A is twice the number of atoms in object B. Suppose the temperature of both the objects is the same, that is, the average kinetic energy of atoms in A is same as that in B. Let us now talk about the heat content of object A and object B. As mentioned earlier, the number of atoms in object A is twice the number of atoms in object B. Thus, the total kinetic energy of atoms in object A will be twice that in object B. Hence, the heat content of object A is twice that of object B, even though they both have the same temperature. We know that when two objects, one hot and another cold, are kept in contact with each other, then both the objects exchange heat. The hot object gives away heat, while the cold object absorbs heat, due to which the temperature of the hot object decreases, while that of the cold object increases. We know that an increase in temperature of an object means an increase in kinetic energy of atoms. Thus, the kinetic energy of atoms in the cold object goes on increasing, while that in the hot object goes on decreasing. This continues, and after a while, a time comes when the average kinetic energies of atoms in both objects become equal. That is, the temperatures of both objects become equal, and the exchange of heat between two objects stops. You might have seen when someone at home gets high fever, mother puts folded cloth strips soaked in cold water on the forehead of the person. Do you know the reason behind this? Correct. Wet strips soaked in cold water being at low temperature absorb heat from the person having fever. Due to exchange of heat, the body temperature of the person having fever decreases. Come, now it's time to perform an interesting activity. Let us take two steel vessels A and B of the same capacity. Now, let us pour a glass of water in vessel A and 2 glasses of water in vessel B. Let us now measure the temperature of water. Water in both the vessels are at the same temperature. It is 28 degrees Celsius. Let us immerse the thermometer in vessel A using stand. Now let us heat the water in vessel A using a spirit lamp till the temperature of water rises by 10 degrees Celsius. At the same time, start the stopwatch. Note down the time taken to raise its temperature by 10 degrees Celsius. Now let us heat the water in vessel B and start the stopwatch. Let us now note down the time taken to attain temperature of 38 degrees Celsius. Let us now compare the readings. we observe that more time was required to raise the temperature of water in vessel B. This means that for the same increase in temperature, we had to give more amount of heat to B. From this activity, we can conclude that even though the water in A and B have the same temperature, the amount of heat in B is more than that in A. After this activity, let us now know units of temperature. Temperature is measured in units of degree Celsius, that is degree C, degree Fahrenheit, that is degree F, and Kelvin, that is K. Degree Celsius and degree Fahrenheit are the units of temperature used in daily life, while Kelvin is used in scientific experiments. Let us now see the relation between these three units. Formula 1. Relation between Celsius and Fahrenheit. F minus 32 upon 9 is equal to C upon 5. Formula 2. Relation between Kelvin and Celsius. K is equal to C plus 273.15. Here some specific temperatures are given in three scales. Come, let us verify whether they satisfy these two relations. Also, let us fill appropriate numbers in the blank places. 1. We know that the boiling point of water is 100 degrees Celsius. Let us convert it into degree Fahrenheit using formula F minus 32 upon 9 is equal to C upon 5. Thus, F minus 32 upon 9 is equal to 100 upon 5. Therefore, F minus 32 upon 9 is equal to 20. Therefore, F is equal to 180 plus 32. Therefore, F is equal to 212 degree Fahrenheit. Answer is matching with the value given in the table. Let us now convert it into Kelvin using the formula K is equal to C plus 273.15. Thus, K is equal to 100 plus 273.15. Therefore, K is equal to 373.15 Kelvin. The calculated value is matching with the one given in the table. Next is freezing point of water. 2. We know that the freezing point of water is 0 degrees Celsius. Let us convert it to degree Fahrenheit using the formula F minus 32 upon 9 is equal to C upon 5. Thus, F minus 32 upon 9 is equal to 0 upon 5. Thus, F minus 32 upon 9 is equal to 0. Thus, F minus 32 is equal to 0 into 9, which is equal to 0. And therefore, F is equal to 32. The calculated value is matching with the one given in the table. Let us now convert it into Kelvin using formula K is equal to C plus 273.15. Thus, K is equal to 0 plus 273.15. Therefore, K is equal to 273.15 Kelvin. Let us correct the value in the table to 273.15. Similarly, room temperature given in the three scales can be verified. Next is boiling point of mercury. 4. The boiling point of mercury is 356.7 degrees Celsius. Let us convert it to degree Fahrenheit using formula F minus 32 upon 9 is equal to C upon 5. Thus, F minus 32 upon 9 is equal to 356.7 upon 5. Thus, F minus 32 is equal to 71.34 into 9. Thus, F is equal to 642.06 plus 32. Therefore, F is equal to 674.06. Let us fill the calculated value in the table. Let us now convert it into Kelvin using formula K is equal to C plus 273.15. Thus, K is equal to 356.7 plus 273.15. Therefore, K is equal to 629.85 Kelvin. Let us enter the calculated value in the table. Next is freezing point of mercury. 5. The freezing point of mercury is minus 38.8 degrees Celsius. Let us convert it into degree Fahrenheit using formula F minus 32 upon 9 is equal to C upon 5. Thus, F minus 32 upon 9 is equal to minus 38.8 upon 5. Thus, F minus 32 is equal to minus 7.76 into 9. Thus, F is equal to minus 69.84 plus 32. Therefore, F is equal to minus 37.84. Let us fill the calculated value in the table. Let us now convert it into Kelvin using formula K is equal to C plus 273.15. Thus, K is equal to minus 38.8 plus 273.15. Therefore, K is equal to 234.35 Kelvin. Let us enter the calculated value in the table. Come, let us now solve some numerical examples. Solved examples. 1. How much will the temperature of 68 degree Fahrenheit be in Celsius and Kelvin? Let us first note down the given information. Temperature in Fahrenheit, that is F, is equal to 68. We need to find out temperature in Celsius, that is C, and temperature in Kelvin, that is K. Let us first find out the temperature in degrees Celsius using formula F minus 32 upon 9 is equal to C upon 5. Substituting the given value, we get 68 minus 32 upon 9 is equal to C upon 5. Thus, 36 upon 9 is equal to C upon 5. Thus, 4 into 5 is equal to C. Thus, C is equal to 20 degrees Celsius. Let us now convert degrees Celsius to Kelvin using formula K is equal to C plus 273.15. Substituting the value, we get K is equal to 20 plus 273.15. Thus, K is equal to 293.15 Kelvin. Therefore, the temperature in Celsius is equal to 20 degrees Celsius. and in Kelvin it is equal to 293.15 Kelvin. 2. At what temperature will its value be same in Celsius and in Fahrenheit? If the temperature in Celsius is C and the temperature in Fahrenheit is F, then C and F will be the same. The relation between Fahrenheit and Celsius is given by formula. F minus 32 upon 9 is equal to C upon 5. This can be written as C minus 32 upon 9 is equal to C upon 5. Thus, C minus 32 into 5 is equal to C into 9. On simplifying, we get 5C minus 160 is equal to 9C. Thus, 4C is equal to minus 160. Thus, C is equal to minus 160 upon 4. Therefore, C is equal to minus 40. The temperatures in Celsius and in Fahrenheit will be the same at minus 40 degree. Come, let us now proceed further. Thermometer. When someone at home has fever, we use a thermometer to check the body temperature of the sick person. The thermometer which we use to check body temperature is called clinical thermometer. Different thermometers are used for different purposes. We shall first learn about the working of a thermometer. A thermometer consists of a narrow glass tube which has a bulb at one end. Part of the glass tube and the bulb is filled with a liquid. Earlier, mercury was used to fill a part of the glass tube and the bulb. But if in case the thermometer breaks and the mercury flows out, it might cause harm to human beings or animals that accidentally ingest it. Therefore, mercury has been replaced with alcohol. The rest of the volume of the tube has vacuum and its other end is closed. The bulb containing alcohol is kept in contact with the substance whose temperature is to be measured so that the temperature of liquid in the bulb becomes same as that of the substance. When the temperature of alcohol inside the bulb increases, it expands and thus the level of the alcohol rises in the tube. Using the properties of the expansion of alcohol, the temperature can be obtained from the level of the alcohol. The tube of the thermometer is marked accordingly. Laboratory thermometers have a large range spanning 40 degrees Celsius to 110 degrees Celsius and even larger. Come, let us now discuss about the clinical thermometer. We know that the body temperature of a healthy person is 37 degrees Celsius. Thus, clinical thermometers are designed to measure temperatures between 35 degrees Celsius to 42 degrees Celsius. Nowadays, instead of this type of thermometers, digital thermometers are used for clinical purposes. Digital thermometers are mercury and glass free. A digital thermometer does not work on the principle of the expansion of liquid due to heat. Instead, it has a sensor which can measure the heat coming out from the body directly, and from that, it can measure the temperature of the body. Do you know that a special type of thermometer is used to measure the minimum and maximum temperatures in a day? It is called the maximum minimum thermometer. Come, let us now proceed further. Specific heat. Let us understand what is specific heat. The amount of heat required to increase the temperature of unit mass of a substance through 1 degree is called the specific heat of the substance. It is represented by the symbol C. The SI unit of specific heat is joule per kilogram degree Celsius, and the CGS unit is calorie per gram degree Celsius. Let Q be the amount of heat required to increase the temperature of an object of mass m and specific heat C from initial temperature Ti to final temperature Tf. This amount depends on the mass and specific heat as well as on the increase in temperature and can be written as Q is equal to m into C into Tf minus Ti. Different substances have different specific heats. The specific heats of a few substances are given in this table. We learned that to measure the temperature of an object, a thermometer is used. But do you know what is used to measure heat content of an object? Come, let us know about it. Calorimeter. A calorimeter is used to measure the heat content of an object. Using this equipment, we can measure the heat produced or absorbed in a physical or chemical process. A calorimeter has two vessels, an inner vessel and an outer vessel. This way, no heat can be transferred from the inner to the outer vessel or from the outer to the inner vessel. Thus, the inner vessel is thermally isolated from the surroundings. The inner vessel is made of copper, as copper has low specific heat. The bigger, that is outer container, has a lid made of a bad conductor of heat. The lid has two holes. A thermometer for measuring the temperature is inserted through one hole, and a stirrer for stirring the liquid in the calorimeter is inserted through the other hole. Inside the calorimeter, water at a fixed temperature is placed. This means that the temperature of the inner vessel and that of the water in it is the same. When a hot object, for example say an iron object at higher temperature is placed in water, heat exchange takes place between the hot object, that is iron ball, water, and the calorimeter. The process of exchange of heat stops when all the three, that is, the iron ball, water, and the calorimeter reach the same temperature. As discussed earlier that the calorimeter is thermally isolated from the surroundings, the total heat lost by the hot object, that is iron ball, is equal to the total heat absorbed by the calorimeter and water inside it. If instead of a hot object, a cold object is placed in the calorimeter, then the cold object will receive heat from the water. This exchange of heat will increase the temperature of the cold object, decrease the temperature of water and calorimeter. Suppose the mass of the inner vessel in the calorimeter is mc and its initial temperature is Ti, and the mass of the water in the calorimeter is mw. As we have supposed the initial temperature of calorimeter is Ti, the temperature of water will also be Ti. Suppose we place an object of mass Mo and temperature To in the calorimeter. If the temperature of object To is higher than that of the calorimeter or water Ti, then the object will give away heat to the calorimeter and water. After a while, a time will come when the temperature of all three become the same. Let us assume this final temperature to be Tf. Suppose the total heat given away by the object is Qo. The heat gained by the calorimeter is Qc, and the heat gained by the water QW. Then, the total heat given away by the object, which is QO, will be equal to the sum of the heat gained by the calorimeter QC and by water QW. That is, QO is equal to QC plus QW. We already know that amount of heat, that is QO, QC and QW, depend on mass, specific heat and change in temperature, that is delta T. If the specific heat of the material of calorimeter, water and the object are Cc, Cw and Co respectively, we can write QO is equal to MO into delta TO into CO, where delta TO is equal to TO minus TF. QW is equal to MW into delta TW into CW, where delta TW is equal to TF minus TI. QC is equal to MC into delta TC into CC, where delta TC is equal to TF minus TI, which is equal to delta TW. Substituting these in equation 4, we get MO into delta TO into CO is equal to MC into delta TC into CC plus MW into delta TW into CW, and this is equation 5. We can measure all the masses and temperatures. If we know the specific heats of the material of the calorimeter, that is copper, and that of water, then the value of the specific heat of the object can be calculated using formula 5. Come, let us now solve numerical problems. Solved examples. 1. Suppose the masses of the calorimeter, the water in it, and the hot object made up of copper, which is put in the calorimeter, are the same. The initial temperature of the calorimeter and water is 30 degrees Celsius, and that of the hot object is 60 degrees Celsius. The specific heats of copper and water are 0.09 calorie per gram degree Celsius and 1 calorie per gram degree Celsius respectively. What will be the final temperature of water? Let us first note down the given things. Mass of calorimeter, that is MC, is equal to mass of water, that is MW, which is equal to mass of copper object, MO. As all these quantities are equal, let us call all these notations as M. Initial temperature of calorimeter and water Ti is equal to 30 degrees Celsius. Initial temperature of copper object, that is T0, is equal to 60 degrees Celsius. Specific heat of copper, that is CO, is equal to Cc is equal to 0.09 calorie per gram degree Celsius. Specific heat of water, that is Cw, is equal to 1 calorie per gram degree Celsius. We need to find out the final temperature of water, that is TF. Let us first write down the formula. MO into delta TO into CO is equal to MC into delta TC into CC plus MW into delta TW into CW, which is equal to M into TO minus TF into CO is equal to M into TF minus TI into CC plus M into TF minus TI into CW. Substituting the given values, we get M into 60 minus TF into 0.09 is equal to m into Tf minus 30 into 0.09 plus m into Tf minus 30 into 1. Cancelling m from both the sides and simplifying, we get 60 minus Tf into 0.09 is equal to Tf minus 30.0.09 plus Tf minus 30. Thus, 60 into 0.09 minus Tf into 0.09 is equal to Tf into 0.09 minus 30 into 0.09 plus Tf minus 30. Therefore, 5.4 minus 0.09 Tf is equal to 0.09 Tf minus 2.7 plus Tf minus 30. Therefore, 38.1 is equal to 0.18 Tf plus Tf. Therefore, 38.1 is equal to 1.18 Tf. Therefore, Tf is equal to 38.1 upon 1.18. And therefore, Tf is equal to 32.29 degrees Celsius. So, the final temperature of water will be 32.29 degrees Celsius. Come, let us now proceed to understand the next part. Effects of heat. Expansion and contraction and change of state are the two effects of heat on matter that we learnt in the previous standard. When heat is given to any substance, its temperature increases and it expands. The extent of expansion of a substance depends on the increase in its temperature. Solids, liquids and gases all expand when heat is given to them. In the next part of the chapter, let us study expansion of solids, liquids and gases in detail. Expansion of solids. The linear expansion of a solid is the increase in length of a wire or a rod of a solid due to increase in its temperature. When we increase the temperature of a rod of length L1 from T1 to T2, its length becomes L2. The change in length is proportional to the original length and the increase in temperature delta T, that is T2 minus T1. So we can write the change in length as change in length is directly proportional to the product of original length and change in temperature. This can be written as L2 minus L1 is directly proportional to L1 into delta T. Thus, L2 minus L1 is equal to lambda into L1 into delta T. This is equation 6. Here, lambda is the constant of proportionality and it is called the coefficient of linear expansion of the solid substance. Thus, L2 is equal to L1 into, in bracket, 1 plus lambda into delta T, bracket complete. This is equation 7. Different substances have different coefficients of expansion. From formula 6, we can write the expansion of coefficient as lambda is equal to L2 minus L1 upon L1 into delta T. This is equation 8. From equation 8, the expansion coefficient can be defined as the change in length of a rod of unit length when its temperature is increased by 1 degree. Let us now know about the unit of expansion coefficient. We know that length is expressed in meter and temperature in degrees Celsius. Thus, the unit of expansion coefficient is equal to meter upon meter into degrees Celsius. Cancelling the meter from numerator and denominator, we get the unit of expansion coefficient. It is the inverse of the unit of temperature, that is 1 upon degrees Celsius. The expansion coefficients of some substances are given in this table. If two rods, one of copper and another of aluminium, both having the same length, are set to increase the temperature by the same amount, then the rod of substance having higher expansion coefficient will expand more. Here, coefficient of linear expansion of copper is less than aluminium. Hence, the increase in the length of aluminium will be larger than that of copper. Come, let us now solve some numerical problems based on what we have learned. Solved examples. 1. What will be the increase in length of a steel rod of length 0.5 meter when its temperature is increased by 60 degrees Celsius? The coefficient of linear expansion of steel is 0.000013 1 upon degree Celsius. Let us first note down the given information. Initial length of the steel rod L1 is 0.5 meter. Change in temperature, delta T, is equal to 60 degrees Celsius. Coefficient of linear expansion of steel is 0.000013 1 upon degree Celsius. We need to find out change in length, which is nothing but L2 minus L1, that is delta L. We know that L2 minus L1 is equal to delta L, which is equal to lambda into L1 into delta T. Substituting the given values, we get delta L is equal to 0.000013 into 0.5 into 60. Thus, delta L is equal to 0.00039 meter. Thus, delta L is equal to 0.039 centimeter. Hence, the increase in length of the steel rod will be 0.039 centimeter. Come, let us now proceed further. Areal expansion of solids. When a sheet of solid material is heated, the area of the sheet increases. This is called the areal expansion of solids. When we increase the temperature of a sheet of a solid material having area A1 from T1 to T2, due to which its area becomes A2, then the change in area is given as A2 is equal to A1 into bracket 1 plus sigma into delta T, where sigma is the coefficient of areal expansion of the solid and delta T is the change in temperature. Come, let us now know about the volumetric expansion of solids. Volumetric expansion of solids. When a three-dimensional piece of solid is heated, then it expands on all sides and its volume increases. This is called volumetric expansion of a solid. When we increase the temperature of a three-dimensional piece of solid having volume V1 from T1 to T2, due to which its volume becomes V2, then the change in volume is given as V2 is equal to V1 into bracket 1 plus beta into delta T, where beta is the volumetric coefficient of the solid and delta T is the change in temperature. Do you know, if you have ever observed rails, you might have noticed that they are not continuous. there is a small gap between them at regular intervals. Do you know the reason behind this? The gap is kept to accommodate the change in the length of the rails with change in temperature. If this gap is not kept, then the rails will get distorted due to expansion in summer, which may lead to accidents. Similar to rails, the length of bridges can also increase due to expansion in summer. In Denmark, there is a long Great Belt Bridge of length 18 kilometers, which increases by 4.7 meters in summer. To accommodate this expansion, provision is made in the construction of the bridges. Come, after this interesting information, let us now proceed to understand expansion of liquids. Expansion of liquids. We all know that liquids have no definite shape of their own, but they have a definite volume. So, a volumetric expansion coefficient for a liquid can be defined as V2 is equal to V1 into bracket 1 plus beta into delta T. Here, V2 is the final volume of the liquid. V1 is the initial volume of the liquid. Beta is the volumetric expansion coefficient of the liquid. Delta T is the change in temperature. It is interesting to know that the effect of heat on water is somewhat different from that for other liquids. In the previous grade, we studied about it. Do you remember? Yes. When water at normal temperature starts cooling, its density increases like that of most liquids. But below 4 degrees Celsius, density of water starts decreasing. This means that at 4 degrees Celsius, density of water is the maximum, and on lowering the temperature below 4 degrees Celsius, its density decreases with increase in its volume. It means that when temperature starts falling below 4 degrees Celsius, water undergoes expansion. This is called as anomalous behavior of water. Do you know any instrument which makes use of the expansion of liquids? A thermometer works on the principle that liquids expand on heating. Come, let us now study about expansion of gases. Expansion of gases. Unlike liquids, gases do not even have a fixed volume. A gas expands on heating, but if the gas is kept in a closed box, its volume cannot increase, but its pressure increases. Here, two setups are shown. In the first setup, gas is kept in a closed bottle with a fixed piston, while in the second setup, gas is kept in a bottle which is not closed but has a movable piston attached to its open end. The gas in both the bottles is heated using the burner. Observing these setups, let us now answer one question. 1. Using the formula density is equal to mass upon volume, what will be the effect of heat on the gas kept in the closed bottle? Here, in the first case, the bottle containing gas is with a fixed piston, due to which mass and volume of gas will not change. Thus, density will not change though the gas is being heated. Next question. 2. What will be the effect of heating the gas in the bottle which has a movable piston attached to its open end? In this case, there is a scope for expansion of gas on being heated. That is, the volume of the gas will increase, and as the volume of the gas will increase, its density will decrease. Therefore, the expansion of a gas is measured by keeping its pressure constant. This volumetric expansion coefficient is called the constant pressure expansion coefficient and is given by the formula V2 is equal to V1 in bracket 1 plus beta into delta T. This is equation 12, where V2 is the final volume of the liquid, V1 is the initial volume of the liquid, beta is the constant pressure expansion coefficient of the gas, delta T is the change in temperature.